Welcome to lecture number 3. We're going to wrap up the rest of our chapter 22 today. Now, I should begin by saying, as I alluded to before in our other lectures, sugars can be drawn in both their open chain and cyclic forms. In reality, they exist in both forms in equilibrium. Now, I admit that when I was new to carbohydrate chemistry, this kind of freaked me out. I remember seeing the open chain form of glucose, for example, like this one drawn here in some places. And then in other places I would see this closed chain ring structure of glucose shown here. And I remember feeling very confused and thinking, these are not the same molecule. How can they both be glucose? I felt frustrated because I don't really feel like my teachers explained this to me very well. So now I'm going to explain it to you. In reality, the open chain form of glucose, shown here, does exist in solution in a small amount, but it's in equilibrium with the ringed structure shown here at the right. So how in the world are they the same molecule going back and forth in equilibrium? Well, here's how. What I want you to do is imagine that this green OH that's coming off of carbon 5 in glucose is the same green OH over here. So in other words, if I draw glucose instead of in this open chain form as looking a little bit more kind of like this semi-ring form, and then you imagine this green OH closing on this carbonyl carbon, and then the electrons being thrust up onto this oxygen, and the resulting O- stealing back this hydrogen from this OH. You can see that when it does that, it forms this ring structure shown here to the right. You can then imagine that ring structure going backwards to the open chain structure by just doing the reverse. This green oxygen steals this hydrogen off of the anomeric OH, and then the electrons thrust down to form a double bond, and this opens back up. We go backwards to the open chain form. So in reality, both of these molecules are glucose, and glucose in real life in equilibrium only exists in a small amount as the open chain form and spends most of its time in its ringed form. Now, when a sugar is drawn in a nice 6-membered ring structure, it's called a pyranose form. I'm going to talk in a few slides about something else called the furanose form. This drawing of glucose, you'll notice, shown here to the right, is a nice, neat chair structure. You can also see that stereochemically, glucose has all of its substituents here in the equatorial positions. Because glucose happens to be the sugar that has the right stereochemical configuration at every one of these stereocenters to attain a nice universally equatorial chair conformation, glucose is the most stable and therefore the most abundant aldohexose on Earth. Now, our text often depicts ring structures in a slightly different way from the traditional chair conformation. This other way of drawing ring structures, which is perfectly acceptable, is called a Haworth projection. I want you to notice something about that. Our book has this drawing of glucose shown here, and we can imagine once again the hydroxyl group dangling off of carbon 5, coming here, thrusting its electrons into this carbonyl carbon, and having those electrons go up onto the oxygen, the O- then tearing a proton off of that OH to give me this ringed structure. You'll notice this is not a chair structure. This is a slightly different way of drawing a ring structure. This is called a Haworth projection. It doesn't show us equatorial or axial. Instead, it shows us up and down. You can notice, once again, that all of the OHs that are pointing to the right over here in glucose, along this main carbon spine, are pointing down in the Haworth projection. And the one OH that's pointing to the left in glucose is pointing up. Now, here's the thing I want you guys to pay attention to. When this OH closes here on this carbonyl to eventually form an OH dangling off of carbon 1, it actually can do so equally well in theory from two different directions. If it closes on this carbonyl carbon from the top, then that ends up pointing the OH that's formed here down. But I bet you guys can imagine the OH coming from underneath and it pointing the resulting OH up. So can you see that? You can imagine once again this OH here coming in to that carbonyl carbon from either side. If it comes in from the top, then the resulting OH dangling off of carbon 1 is pointing down. If it comes in from the bottom, then the resulting OH coming off of carbon 1 is pointing up. So when I say that glucose exists in equilibrium between its ringed structure and its open chain form, what I actually should be saying is that it exists in equilibrium between its two different ring structures, these two, and its open chain form. The open chain form of glucose in equilibrium exists at about 0.02%. This form of glucose with the OH pointing down exists in about 36% in equilibrium. And this one with the OH pointing up exists at about 64% in equilibrium. These two different compounds, just so that you know, are called anomers of each other. You'll notice that stereochemically they have the exact same stereochemical configuration at every stereocenter except for this one carbon right here. You also might remember me talking earlier in our previous slide about the word epimers. Epimers are two diastereomers that have the exact same stereochemical configuration every stereocenter except one. Technically, anomers, like those shown here, are also epimers. However, we like to make up new terms for you guys to memorize for no reason. So we use the word anomer to refer specifically to epimers of sugars that differ stereochemically at the anomeric carbon. So the anomeric carbon is carbon 1, this carbon that began as being the carbonyl carbon upon which the OH closed to form these two rings. So this anomeric carbon, if we have the opposite stereoconfiguration between two different structures, these two different structures are called anomers of each other. One other thing that I should tell you is that this entire process of interconverting between these two ringed forms and the straight chain form is called mutarotation. Some sugars, like D-fructose, shown here, have the ability to cyclize from their open chain forms to a 6-membered ring or to a 5-membered ring and then back. So as I mentioned before, the 6-membered ring is called a pyranose form, and the 5-membered ring is called a furanose form. So I'll explain how that works. You can imagine for D-fructose, if this green OH closes here on the anomeric carbon, carbon 2, fructose is a little different from glucose because it's a ketose. It's got a ketone in it instead of being an aldose where you've got an aldehyde on the end. This green OH closes on the carbonyl carbon, it forms a 5-membered ring, this furanose ring. If instead this pink OH over here dangling off of carbon 6, if this pink OH closes, that actually forms a 6-membered ring, this pyranose ring. So in reality, how does D-fructose exist in solution? It actually exists going back and forth between both of these two ring structures, the pyranose form and the furanose form, with the open chain form existing transiently as an intermediate between the two. As I already discussed 2 slides ago, sugars can cyclize back and forth between their open chain and ringed forms in 2 different ways. One is by putting the OH going down. So you can see if this oxygen closes on the anomeric carbon in a way that points the OH going down, we get one form. And the other is pointing the OH up. And as I did say 2 slides ago, these 2 rings, 1 and 2, are called anomers of each other. This process of going back and forth in equilibrium between these 2 rings is called mutarotation. And of course, carbon 1 is called the anomeric carbon. Now this brings up an important point. I need to teach you this principle called alpha versus beta sugars. You'll notice if we look at this anomer 1, that the OH here, the anomeric OH, is pointing down, and this CH2OH that's dangling off of carbon 5 in the ring is pointing up. These 2 groups, the CH2OH up here and this OH down here, are trans to each other in this anomer. In this anomer over here, the CH2OH is pointing up, and this OH is pointing up also. So these two groups are cis to each other. Now, as it turns out, we have a name for this. If you have an anomer where the anomeric OH is trans to the CH2OH in the pyranose form, it is called an alpha anomer. If you have the anomer where the CH2OH and the OH are cis to each other, they are called beta anomers. This principle is going to become very important shortly when I talk and refer to alpha sugars versus beta sugars. And this brings us to a magical question. How can I, on paper, go back and forth between open chain and ring forms of carbohydrates? In other words, if I'm given an open chain structure of a sugar like this one shown here for D-mannose, and if my teacher asks me to draw it in its ringed form, can I do it? And if so, how? Well, I'm disappointingly not going to give you the answer to this question here. But I promise you that we will do it together as a class. To prepare for that, however, I'm going to direct you to the latter portion of section 12 from this chapter in your text. Can you take this open chain form of D-mannose and draw it in its ringed pyranose form? Can you? I'll let you try. And now we arrive at this magical word called glycoside. Glycoside. The killing of so anyway, there's this magical reaction that we can do to selectively replace an anomeric OH with an OR group, where R is an alkyl group. So in this example that I have here, we replace the OH with a methoxy group by treating this sugar with methanol and acid. What we end up getting is two different isomers, one being alpha, where these two groups are trans. That's how I remember alpha, by the way. Trans has an A in it. Alpha. Ans. Trans. And these two are cis to each other, so beta. These compounds are called glycosides. Now, glycosides in reality are really just carbohydrate acetals. If you can't remember what an acetal is, please review chapter 18. Now I'm going to show you the mechanism by which glycosides are formed. You might remember, to form a glycoside, I take my sugar, I treat it with an acid, and then I eventually treat it with an alcohol, and I replace the OH with an OR, where R is an alkyl chain. The mechanism by which this proceeds is the following. The anomeric OH reaches out and steals a proton from the acid to generate this protonated form. At this stage, this anomeric oxygen right here thrusts its electrons down in here to form a double bond and kicks off water as a leaving group. That gives me this intermediate. Now look at this intermediate. I've got this oxygen that has 3 bonds and a positive charge. This carbon right here is obviously going to be a very hot spot for nucleophilic attack. So at this stage, my alcohol, whatever alcohol I've happened to choose, can come in and attack and form a bond at this carbon, and upon doing so, push these electrons back into this oxygen to neutralize the charge. Once again, you can imagine this OH can come from either direction, the top or the bottom. If it comes from the top, then it ends up giving us this intermediate. And eventually, that will get deprotonated to give me my beta glycoside. Once again, the beta anomer is where these two groups are cis to each other. Now you can just as easily imagine the alcohol coming in from underneath to form a bond. If it comes in from underneath, then we get this isomer, and this isomer will eventually get deprotonated to form this alpha glycoside. Alpha glycosides, strangely, are the major product, even though they have an axial OR group instead of an equatorial. I'm not going to tell you in too much depth as to why. It's caused by something called the anomeric effect, but it is interesting to note. Now, there are several polysaccharides that are extremely important and essential to life on our planet. One of these is starch, which is technically a mixture of two different polysaccharides, amylose and amylopectin. So starch, once again, is a sugar mixture that's made up of 20% amylose and 80% amylopectin. While I don't require you to know the structures of amylose and amylopectin for memory, I do want to show them to you so that you can say that you've seen them. Here's the structure of amylose. As you can see, amylose is a polymer of multiple glucose molecules all bound together in a 1, 2, 3, 4. So a 1 to 4 relationship with this oxygen pointing down. You'll notice this oxygen is trans to the CH2OH. Therefore, this is an alpha linkage. So once again, amylose is a glucose polymer of 1, 4 alpha linked glucose molecules. Here's the structure of amylopectin. Amylopectin is a glucose molecule that has branch points at position 1, position 4, and also on this CH2OH, this oxygen is bonded periodically to other glucose molecules at position 1. Can you see that? So it's got a little bit more branching than we have in amylose. So here's amylopectin. One thing I want you to pay attention to is the fact that amylopectin also has all alpha linkages. So you'll notice that every one of these oxygens is trans to the CH2 at carbon 6. They're trans, therefore they are alpha. You see that? So this is amylopectin's structure. I want to just reiterate. Starch is actually a mixture of 20% amylose and 80% amylopectin. As I mentioned in our first video lecture for this chapter, cellulose is another important polysaccharide made up of thousands of glucose molecules linked together in a 1,4 bonding pattern, similar to amylose. In contrast with amylose and amylopectin, however, cellulose's branching pattern is all beta. So you can see this anomeric oxygen here is cis to the CH2OHs. Because they're cis to each other, they are all beta. This places this anomeric oxygen equatorial relative to the ring. Now, because cellulose has this beta branching pattern, individual molecules of cellulose are able to sit and stack more tightly on top of each other than amylose or amylopectin. This gives cellulose greater rigidity and strength than starch. And that's why nature uses cellulose to provide strength, rigidity, and structure to plants. One interesting fact that you should know is that all mammals have the enzymes necessary to break 1,4 alpha linkages in sugar polymers. However, we do not have the enzyme that breaks 1,4 beta linkages. That's why we mammals can obtain the glucose that we need by eating starch in our diets, because we have the enzymes necessary to break those alpha linkages. But we do not have the enzyme necessary to break beta linkages present in cellulose. That's why we cannot obtain the glucose that we need by eating cellulose. Think about it. When was the last time that you got any nutrition from eating a newspaper? You didn't, because you don't have the enzymes to do it. Now, you should know that bacteria do possess the enzyme necessary to break 1,4 beta linkages in cellulose. Grazing animals like cows and horses have these bacteria in their digestive tracts, which is why they're able to obtain the glucose they need by eating grass, which is made up almost completely of cellulose. Also, termites have bacteria in their digestive tracts that also enable them to obtain glucose by eating wood, which is also made up heavily of cellulose. One question that might elicit wonder and amazement is, why do people have different blood types? And what really causes this difference? Be prepared to be dazzled. And by dazzled, I mean bored, because I am about to tell you. You see, polysaccharides are extremely important in helping our cells communicate with each other. Nearly all of our cells' phospholipid membranes are coated with various sugar polymers that facilitate intercellular communication. Our blood cells' surfaces are coated with polysaccharides that allow them to communicate with each other. The differences between the 4 human blood types, which are A, B, AB, and O, are caused by our blood cell surfaces being coated with different polysaccharides. So a person who has blood type A has blood cells that are coated with this particular pattern of polysaccharides. N-acetylglucosamine attached to the phospholipid membrane with D-glucose bounded to L-fucose, and then this N-acetyl-D-galactosamine dangling off of it. People who have type B blood have this polysaccharide pattern coming off of their surface. People who have type AB blood actually have mixtures of both type A and type B together. People with type O blood do not have the N-acetyl-D-galactosamine or D-galactose dangling off of it. All they have is this sugar pattern coming off of the surface of their blood cells. This is really interesting because you'll notice that anyone who has type AB blood has cells that are coated with all the stuff that you see in type A and all the stuff that you see in type B. That means that someone who has type AB blood is a universal acceptor. So they can receive blood from someone with type A, and their blood cells will recognize this type of sugar on the surface of their blood cells. They can receive blood from people of type B and be just fine as well, because people with type AB blood have both type A and type B sugar patterns on the surfaces of their cells. Type O lacks these extra appendages dangling off of them, which means that type O can donate to anyone. Anyone who has type A or type B can accept type O, because type O has the exact same internal structure as type A and type B. Unfortunately, type O can only receive from type O. If you tried to give type A to a person with type O blood, the person with type O blood, their bodies would see this extra N-acetyl-D-galactosamine as a foreign invader and would not accept it. Similar would occur with type B. So once again, that explains why someone who has type AB blood is a universal acceptor, and someone who has type O blood is a universal donor. I now want to just tell you a story of synthetic sweeteners because I think it's really interesting. But I'm probably not going to ask you any soul-searching questions about them on exams or quizzes. For a molecule to taste sweet, it has to bind to a receptor found on taste bud and cells of our tongues, which then sends a nervous signal to our brain that registers that molecule as being sweet. Believe it or not, different sugars actually differ in their level of sweetness, compared with the sweetness of glucose, which is assigned a sweetness value of 1.0. Sucrose's sweetness value is 1.45. Fructose is even higher, 1.65, which explains why we frequently see high fructose corn syrup being used as a sweetening agent in foods. Now here are several synthetic sweeteners that you can see. Interestingly, with the exception of sucralose shown here, none of them really have carbohydrate structures. Saccharin over here, which is also known as sweeten low and was the first synthetic sweetener to be discovered. It's about 300 times sweeter than glucose and has very few calories. Dulcin, shown here, is a synthetic sweetener discovered a little bit later. It has the advantage over saccharin of not possessing the bitter metallic aftertaste. However, it was later banned because of toxicity. Sodium cyclamate down here is another synthetic sweetener that was also later banned in the U.S. because it was found that large amounts of it cause liver cancer in mice. Aspartame, right here, which is also known as NutraSweet, is about 200 times sweeter than sucrose and was approved by the FDA back in 1981. You know, I actually remember as a kid when NutraSweet gradually began to gain popularity and was being propagated through intense advertising campaigns for diet sodas and a number of other things. I actually remember that. NutraSweet was new and everyone thought it was just really exciting. And now it's slightly old news, but we still use it a lot. Now, acesulfame potassium right here was approved in 1988. It's about 200 times sweeter than glucose, has less aftertaste than saccharin, and is more stable than NutraSweet at high temperatures. Now, sucralose down here, which is also known as Splenda, among other names, is 600 times sweeter than glucose, and was just approved back in 1991. It maintains sweetness after longer storage periods and can be used at high baking temperatures. It's made by selectively replacing 3 of sucrose's OH groups with chlorines. The body doesn't recognize sucralose as a carbohydrate, so it gets eliminated from the body unchanged. Hence, we can eat sucralose, it tastes sweet, and not gain all of the caloric intake that we would from traditional carbohydrates. Well, that ends my lecture for this chapter. Thank you guys for hanging in there and listening to all of this. I realized that I didn't have as many funny stories or personal anecdotes in this section, and I'm sorry that it might have been a little bit more boring. But don't worry, I promise to make amends for that in our later chapter lectures, which you hopefully will enjoy. I'll see you then.